Do you want incredible stories? I have one for you. Absolutely fantastic. This is a story about an amazing mechanism through which our entire world is put together and seems so familiar to us. But don't be misled by this familiar simplicity. I will dispel your illusions about the simplicity of the world, and you will see that you live in a wonderland. And let my cat Martin be your Cheshire cat, smiling at you as wide as the sausage clamped in his teeth. So listen to the story that began in 1801, when the English scientist Thomas Young conducted an experiment aimed at proving that light is a wave, similar to a radio wave. At that time, there were two theories in the scientific community. One was the theory of Christiaan Huygens, which claimed that light is a wave that propagates through a hypothetical medium called the ether. The popularity of the theory can be judged even by the fact that we still use the word ether. And back then it was believed that nothing could be transmitted through a vacuum. If electricity is transmitted through conductors, then light must also pass through something. And they invented the ether, a substance conductor that does not manifest itself in any other way. Hello to dark matter. The alternative view was the theory of Isaac Newton, according to which light consists of particles, corpuscles. Young was a supporter of the wave theory, and to confirm it experimentally, he devised a special method. He created a device that consisted of a wave source emitting a narrow beam of light, a screen where the results were recorded, and a partition between them with two parallel slits. When light passed through these slits, it split into two separate beams, which then intersected on a distant screen. Young carefully observed the resulting pattern and saw an interference pattern consisting of alternating light and dark bands. This alternation indicated that the light waves overlapped, creating regions of reinforcement, light bands, and attenuation, dark bands. Such an effect was possible only if light had a wave nature, allowing waves to interact in this way. If light consisted of particles, the screen would show just two vertical bands corresponding to the two slits through which the light passed, and there would be no interference patterns. So for the scientists of that time, the nature of light became clearer. But what about electrons? At the beginning of the 20th century, scientists imagined the electron as a tiny particle of matter with a negative charge. They used this particle model to explain many phenomena, but some observations hinted that the electron might have other properties. To find out, in 1927, American physicists Davisson and Lester Germer conducted a decisive experiment. Davisson and Germer used an electron gun capable of emitting a narrow beam of electrons with high precision. They directed this beam onto the surface of a nickel crystal, which acted as a diffraction grating. The nickel crystal scattered the electrons in different directions, similar to how a diffraction grating scatters light waves. After interacting with the crystal, the electrons hit a detector, creating a diffraction pattern with characteristic alternating intense and weak bands, similar to those created by light waves. This indicated that electrons also have wave properties. Thus, it was concluded that an electron is not only a particle, but also a wave, significantly changing the understanding of the nature of matter at the quantum level. But if both the photon and the electron are waves, then Young's double-slit experiment can also be conducted with electrons. In 1961, German physicist Klaus Johnson conducted just such an experiment, which became known as the electron double-slit experiment. An electron gun was used, emitting beams of electrons. These electrons were directed at a screen with two very narrow parallel slits. When the electrons passed through these slits, they interacted with each other like waves on water, forming interference bands on a detector placed behind the slits. Diffraction bands, or interference bands, appear as a result of wave interference. When waves reinforce each other, light bands form, and when they cancel out, dark bands appear. But Johnson decided to go further. He tried shooting not a beam, but one electron at a time. After shooting some electrons, Klaus evaluated the result, and here he had to take off and wipe his glasses. The same interference bands proudly adorned the screen. But this was impossible. Interference bands are formed only when electrons pass through both slits simultaneously and interact with each other. The scientist closed one slit and shot the electrons both individually and in groups. The detector showed just a vertical band. As soon as he opened the second slit, interference bands appeared again. Klaus decided to understand what was flying through those slits and placed an electron detector. The detector noted through which slit the electron passed. To avoid confusion, let's call this detector a camera. Turning on the device with the camera and shooting some electrons, Klaus had to wipe his glasses again. The camera perfectly recorded the passing electrons, but the screen proudly displayed two vertical bands, no matter how terribly it sounded in another context. This indicated that the electron behaves like a particle. Klaus turned off the camera again and repeated the experiment. What he saw again made him want to wipe his glasses, but it didn't work, because Klaus Johnson remembered that he never wore glasses. Without recording with the camera which slit the electron passed through, the result was again interference bands. Thus, it turned out that observing the electron changed its behavior. But how is this possible? Cat Martin approached me and ultimatumly demanded to stop telling fairy tales. Well, okay. In fact, scientists knew about such strange behavior of quantum particles before. In 1900, Max Planck explained the spectrum of black body radiation by introducing the idea of energy quanta. A black body is a hypothetical object that absorbs all electromagnetic radiation falling on it and does not reflect any light. Planck showed that to explain the radiation of such a body, it is necessary to assume that energy is emitted and absorbed not continuously but in discrete portions, which he called quanta. In 1905, Albert Einstein explained the photoelectric effect using the concept of light quanta, photons. The photoelectric effect is that light, falling on certain materials, knocks out electrons from them. Einstein proved that this is possible only if light consists of individual particles, photons, confirming the corpuscular properties of light. In 1913, Niels Bohr proposed a model of the atom in which electrons move in defined orbits around the nucleus, and the transition between these orbits is accompanied by the emission or absorption of a quantum of energy. This explained why atoms emit or absorb energy only at certain frequencies. In 1914, James Franck and Gustav Hertz conducted experiments that confirmed the existence of discrete energy levels in atoms, consistent with Bohr's theory. They proved that electrons can transition between energy levels by absorbing or emitting a precisely defined amount of energy. In 1927, Werner Heisenberg formulated the uncertainty principle, which states that it is impossible to simultaneously measure both the coordinates and the momentum of a particle accurately. Let's stop here for a more detailed explanation. If you throw a ball, you can determine its speed and position in space at any moment. This does not work with elementary particles. Elementary particles are in a state of superposition, that is, a state in which they are both a wave and a particle simultaneously. Heisenberg believed that the act of measurement affects the elementary particle, destroying its superposition. In other words, the act of measurement is an interaction that changes the particle's state, forcing it to choose one of the possible positions. But it was believed that all these states are possible only for elementary particles and do not extend to more complex systems. As we will see later, this was still a mistake. To describe the behavior of quantum particles, a theory was proposed called the Copenhagen interpretation. It states that particles, such as electrons or photons, can exist in multiple states simultaneously until they are measured. This means that, for example, an electron can be both here and there simultaneously. But as soon as we try to measure or observe it, it chooses one specific state. This process is called wave function collapse. The Copenhagen interpretation also introduces the concept of the uncertainty principle, according to which we cannot know both the position and speed of a particle precisely. In other words, the more accurately we know one, the less we know about the other. This theory helps explain the strange and unpredictable phenomena of the quantum world, but it also raises many philosophical questions about the nature of reality and the role of the observer in quantum mechanics. So, elementary particles exist in a strange state called superposition. In this state, they are simultaneously in all the places where they could physically be. Only an observer or interaction with the particle fixes it in a specific position, making it real in our world. In the double slit experiment, when a single electron was shot from the electron gun, it moved in all possible directions simultaneously, including passing through both slits simultaneously. This amazing state allowed the electron to interact with itself, forming an interference pattern on the detector. And this applies not only to particles moving in space, but also to any microworld processes, such as the decay of an atomic nucleus. If you do not observe the atom and do not measure its state, it will be in superposition, that is, simultaneously decayed and not decayed. For the human mind, this process is absolutely non-obvious. It takes time for the brain to adapt to new facts. Therefore, not all scientists supported the postulates of the Copenhagen interpretation. For example, Erwin Schrödinger created his famous thought experiment to show the paradoxical nature of quantum superposition states. Briefly, I'll remind you what it is about. Imagine we have a cat that we place in a completely closed box where no one can see inside. In this box, there is also a device consisting of a radioactive element, a Geiger counter, a device for detecting radiation, a hammer, and a small glass vial of poison. The radioactive material is arranged so that it may or may not decay within an hour. If it decays, the Geiger counter will immediately detect it and activate a mechanism that will cause the hammer to break the vial. The poison will be released and the cat will die. If the radioactive material does not decay, nothing will happen and the cat will remain alive. According to quantum mechanics, the radioactive material can exist in two states at the same time, decayed and not decayed. This means that until we open the box and look inside, we cannot know whether the cat is alive or dead. Therefore, according to quantum mechanics, the cat is in a superposition. It is considered both alive and dead at the same time. Schrödinger created this experiment to show how strange and non-obvious the behavior of quantum particles can be when we try to apply quantum principles to larger things, such as a cat. It was an attempt to show that quantum mechanics can lead to very strange and illogical results when we apply it to our everyday macroscopic world. But the most interesting thing is how wrong he was. Schrödinger did not anticipate that his thought experiment would become one of the most vivid illustrations of the strange and mysterious world of quantum mechanics, confirming that at the level of elementary particles, our world operates under completely different rules. And the weirdness was just beginning. When I was writing this script, I had to make Schrödinger's dog the subject of the experiment. The thing is, my cat Martin took my slippers hostage and promised to destroy them with all available feline methods if I didn't stop tormenting cats, even hypothetical ones. Everything returned to a scientific course only when the terrorist fell asleep. Scientists believe that all the processes described above only happen to elementary particles in the microworld, and that such phenomena cannot occur in our everyday life. The reason for such confidence I did not understand. It was obvious that something was wrong. What is this inexplicable boundary between the quantum world and the macro world? It was also believed that the change in the state of a particle during measurement in the quantum world is explained by the fact that the energy of interaction, which acts on the microparticle during measurement, knocks it out of the state of superposition. And it is impossible to measure any parameters of a particle without interacting with it. Cracks in the boundary between the quantum world and our macro world began to appear after new experiments were conducted. In 1999, a group of scientists led by Anton Zeilinger from the University of Vienna conducted another double-slit experiment. But this time, the scientists used not electrons, but fullerene molecules. Fullerenes are fairly large molecules consisting of 60 carbon atoms and shaped like a football. "Well done, scientists," summed up Cat Martin, experimenting with his ball. In the new double-slit experiment, fullerene molecules were evaporated in a vacuum, creating a beam of individual molecules. This beam was directed at a screen with two narrow slits. After passing through the slits, the fullerene molecules fell onto a second screen where the result was recorded. As in the case of the double-slit experiment for light or electrons, an interference pattern appeared on the screen, a series of alternating light and dark bands. This showed that the molecules behaved like waves, passing through both slits simultaneously and interacting with each other. This experiment became an important confirmation that even large molecules, such as fullerenes, have a quantum wave nature. It demonstrated that quantum mechanics applies not only to small particles like electrons, but also to much larger molecules. Naturally, the question arises, if this is still the microworld, where should the boundary between the microworld and the macroworld be drawn? And further experiments showed that there is no such boundary. In 2020, a group of scientists from the University of Vienna, led by Simon Groblacher, conducted an experiment to test whether large objects can exhibit quantum properties. They took a tiny metal plate and cooled it to very low temperatures, close to absolute zero. This needed to be done to stop all thermal motions in the plate and reveal its quantum properties. The fact is that thermal radiation is essentially no different from light, and for the experiment to be successful, there should be no interactions, even heat transfer, between the plate and the research chamber. So after that, the scientists used lasers to make the plate vibrate. Lasers allow for very precise control of the plate's movements. Then, using extremely sensitive instruments, they observed its vibrations. The scientists found that the plate was simultaneously in two different states of vibration. That is, it vibrated, moving back and forth at the same time, as if it were in two places simultaneously. This phenomenon is called quantum superposition, and it was detected in a macro object. So the hypothetical Schrödinger's cat is not just a fairy tale, but a theoretically possible situation. Now let's think about this. We see that both micro and macro objects have the ability to create superpositions relative to another system. It looks like unrelated systems create all variants of their interaction. Then one of the variants becomes reality, and the rest disappear. This happens according to the Copenhagen interpretation. The drawback of this interpretation is that it is impossible to fully explain what superposition is and how it arises. But there are other options. There is also the theory of the multiverse, proposed by Hugh Everett. I talked about it in a video about quantum immortality. According to this theory, all possible variants of events are created in separate universes. That is, When shooting an electron towards two slits, universes appear where the electron passes through both the right and the left slit and doesn't hit the slits, hitting the plate instead. This theory also has its drawbacks, and it's not even that somewhere out there, not clearly where, entire universes are created with which we cannot interact. The question is that, as we have found, two macro systems can be in superposition relative to each other. It turns out that the whole world is one macro system, and for example, the membrane in the last experiment is another. And our world must also create all the variants relative to the membrane as it does relative to each variant of the world. And this is even hard to imagine. So the question of how all this happens is still open. Although there are many other perspectives. I was surprised at how many physicists consider consciousness an important factor in quantum effects. Stephen Hawking believed that the wave function does not describe reality itself as something that exists independently of our perception, but only what we know about this reality, and that everything is clear here and there's no need to discuss it. Once Hawking even said, "When I hear about Schrödinger's cat, I reach for my gun," jokingly showing how unimportant it is to even talk about superposition. Well, okay. But how can we interpret the even more fascinating experiments called delayed choice experiments or quantum erasers? The theoretical concept of the delayed choice experiment was proposed by Archibald Wheeler, a prominent American physicist, in 1978. Wheeler suggested that the choice to set up or not set up the camera in the double-slit experiment could be made after the particle has passed through the slits, but before it reaches the screen. This means that the observation or lack of it happens retroactively. Obviously, it was impossible to do this by ordinary methods, since the very idea seemed unrealizable. But, using so-called quantum entanglement, such an experiment was later conducted. And more than once. And the results are insane. I will not describe the setup itself so as not to confuse and distract the viewers, because the setup was quite complex, but I will roughly describe the results obtained. Imagine the already known double-slit experiment using a camera, but the camera, after taking a measurement, packs the photo in an envelope and seals it. The screen, where the particles hit and create a pattern, is also sealed in an opaque envelope. We start the experiment. The gun shoots electrons a number of times. We get two piles of sealed envelopes. One pile is the images from the camera, and the other is just one envelope with the screen. The first option for our actions. First, we open the envelopes from the camera, see where the electrons were flying. Then we open the envelope with the final screen, and it shows two bands. No interference. That is, the observer changed the state of the electrons in flight, and they behaved like particles. The second option. First, we open the envelope with the screen. Again, we see two bands. Well, everything is correct. Even without opening the camera envelopes, it is clear that the observer effect is present. But there is one more option. The third option. We take the whole batch of camera shots and throw them in the stove, where they burn without a trace. After that, we open the envelope with the screen and see a diffraction pattern. Can you imagine? The universe understands that the observer did not see the trajectory of the electron and did not manifest it in space, so the electron remained as a wave, that is, multivariant, and no interactions with the camera disrupted the wave function. But this is an important fact that allows us to understand how everything works in the quantum world. If now you are confused and unable to believe this, it's okay. Over time, it will pass. The quantum world, and not only the quantum one, hides such surprises that tear apart our usual intuitive world, or rather, our intuitive view of the world. Many physicists did not believe the results of the experiment and began to repeat them to verify Wheeler's theoretical predictions. The implementation of such experiments in laboratory conditions confirmed the principles of quantum mechanics demonstrated in the delayed choice concept. So once again, how can this be understood? It turns out that the data on the screen changes when we burn the envelopes. Or were they always like that because the universe somehow knew we would burn them? Let's try to explain this using the Copenhagen interpretation. This interpretation states that a quantum system is in superposition until observed, and the act of measurement forces the system to collapse into one of the possible states. In the case of the delayed choice experiment, the choice to observe or not observe the particle influences its previous behavior. But nevertheless, the fact of attempting to observe was there, although it did not lead to an observation result. That is, the electrons somehow go back in time and draw the correct picture. Interesting, but somewhat strange. That is, the idea that the superposition of parts is influenced, for example, by the light from the camera, does not work. And what about the many worlds interpretation? Perhaps we automatically jump to a universe where we burn the envelopes and an interference pattern appears on the screen, and the universe variant where we burn the envelopes and two bands remain on the screen is eaten by Langoliers from the eponymous book by Stephen King. That is why this experiment remains a mystery that no one has yet answered in clear words. At least, I have not found such an explanation. Then I'll tell you my version. It seems that the world is created by cause and effect relationships. That is, let's imagine that there are two completely isolated objects, for example, two balls flying in absolute emptiness. "Oh, balls again," said Cat Martin and took up his second ball. So these balls fly, absolutely not interacting with each other. And in such a state of non-interaction, both systems, or balls, are in superposition relative to each other. But it happens that these balls collide somewhere and fly off in different directions. Now they are connected by information about how hard they hit each other, where they flew off to, and so on. That is, one ball knows where the other should be after some time. Moreover, by measuring how one ball flies, you can conclude the movement of the other. Those who already know about quantum effects probably guessed where I'm leading. Here I need to talk about another quantum effect, particle entanglement. It is believed that when two elementary particles, for example photons, collide and fly apart, a strange connection appears between them. They are still in superposition relative to us, the observers, but if we measure the state of one of the particles, the state of the other immediately fixes. And this is not because these states are fixed for them. There are experiments proving that there is no initial fixation. Moreover, this effect is widely known and used in quantum computers and encryption. The field is still young, but it seems that there will be more applications. And it does not matter how far apart the particles are. The second particle immediately feels that the first one has been measured and fixed. Albert Einstein called the phenomenon of quantum entanglement spooky action at a distance. And indeed, if we rely on the Copenhagen interpretation of quantum mechanics and Einstein's theories, it is indeed some kind of horror. The particles seem to communicate with each other, and at superluminal speeds, which doesn't fit into any frameworks at all. And now let's return to our balls. So the two balls collided and flew apart, and their joint system is connected. They exist for each other in reality. But what about the third ball that also flew nearby? For it, the first two remained in superposition, because they could also collide with each other at any point with any force and angle. The third ball knows nothing about this. So for it, the first two are in superposition. But everything changes if the third ball interacts with any of the previous connected ones. For example, the third ball somehow can measure speed, and measures the speed of the first ball. And based on this information, as well as the information that the first and second balls collided, it is possible to understand where the second ball is. And therefore, this second ball also loses superposition relative to the new ball, and its movement will be predictable during measurement. Here arises an interesting theoretical question. And if the third ball knows nothing about the first and second being connected, will the second ball lose superposition relative to the third after the third collides with the first? But this can only be speculated, although theoretical studies of these issues could say a lot about the nature of the universe. And one more thing. The quantum eraser effect can also be easily explained from this perspective. When we burn the envelopes, the observer disappears, and nothing can connect our world with the particle. The exchange of information between the observer and the particle did not take place, so the particle behaves like a wave. That is, it is in all possible places and states at the same time. And it does not matter that the destruction of information occurred later. The systems did not connect through information. In fact, Everett's many worlds theory is best suited to explain all these quantum wonders. But there is one question. What about the wave function? Because the wave function is essentially multivariability, that is, many universes in one particle, but we observe it in such a state in our, specifically one of many universes, so something does not add up. Either the universes can interpenetrate or unrelated systems can be multivariant in one universe. And only one variant is chosen, and the rest disappear into oblivion. It seems that the world is governed by cause and effect relationships, and even the information about a possible cause and effect relationship. Any independent systems will be in superposition relative to each other until they interact. After that, these systems become one system. However, their joint system can still be in superposition relative to all other independent systems. Why don't we see this in the macro world? Because the more micro objects are connected into one system, the larger this system becomes. And the larger it is, the harder it is for independent systems not to connect with it. Various types of radiation connect systems by transmitting information between them. Thus, the world is created from probabilities. Maybe there is only one variant of the world, or maybe other variants exist somewhere nearby. In the case of microscopic particles, it is easier for them to be in superposition. They are in a rarefied space where no beams or interactions can affect them, leaving them in all possible variants. So it is not surprising that some scientists believe that our world is some kind of computer simulation, because everything is related to the possibility of transmitting information about states. And we are already used to the fact that information is a computer. But this has not been proven yet, and we can only think and speculate about how everything works. If you are interested in such information, I recommend reading the books, the links to which I have posted in the first comment. And Cat Martin often reminds me of multivariability. When I have to get up to go to the bathroom at night, I have to make my way through the darkness past Martin the cat in superposition, who at any moment can materialize his tail under my foot. And the result of destroying Martin's superposition will be a cat hysteria throughout the house and my scratched legs. Hang in there, subscribe, comment, read books,